Hi again, we're back. Hopefully it's a different day for you. You don't want to do all your homework at once. By the way, it's freezing in this room. This is still Friday for me, and it's 65 degrees. I'm freezing, and I can't wait to go to Florida. By the time you're watching this, you will be imagining that I already am in a warmer place, and super happy about that. This time, we're going to go over the notes for 7.2, and we're only going to cover part of section 7.2 here. The rest we'll cover when we get back to school next week. This section is not about areas between two curves like we had in the last segment, but instead taking that area and using a third dimension to make a volume. So our third dimension typically has one of two different outcomes, either a straight third dimension that comes straight out. And you have to almost imagine if we have the XY axis flat here, and we have a curve on it with a top and a bottom. Our area is like, this Post-it note behind me. But if I create a volume out of it, I'm going to create a volume by extending straight out. And we'll see some different examples of this. I have hopefully some animations that will help you see what happens, what it looks like. The pictures on your notes, though, try to describe the three-dimensional shapes that we're going to be creating today. We're only going to be doing one style, this popping out from the paper kind of third dimension. Next time we come together, we're going to talk about a different kind of third dimension, and that comes from a rotation or a spinning, and we'll talk about it later, but it's almost like what you see on the table legs or chair legs in your house, and they take a curve and they spin it, and then they get this vase-shaped volume, and we're going to create those. Those are volumes by rotation. So let's go to the PowerPoint that I have and have your calculators again. We may go to the calculator to get some answers for our integrals. We're using integrals again today. And volume, integrating to create volumes. So this section, 7.2, has several parts to it. The part that I'm going to focus on today is the cross-section method. We also will go into the washer method and think of what a washer looks like. It's a donut, like a CD shape. There is a third method we're not touching. You don't need to know it for the AP test, but it's a shell, almost like a toilet paper tube, and creating a whole bunch of shells to make a volume. But we'll talk about that more when we get back to school. So the volume of a solid. If we're going to find a volume of a solid, I want you to think about stacking thin prisms. Now, really, I want you to think of stacking up CDs on top of each other. And when you stack up all those CDs on top of each other, you get a volume. And the volume is equal to the area of one CD, that face of the CD, times the height of all of the stacked up CDs, or a bunch of individual baby heights. And we are going to call them sometimes bases because we'll turn it sideways. That little baby height is an increment of x or y, and therefore we have that dx or that dy coming back at us. If we add them all up, we have a volume. So we'll use the integral to represent the sum or the accumulation of all of the thin CD pieces. The other thing I like to use here as an example, this sounds kind of silly, but a loaf of bread. Now, if you know what a loaf of bread looks like when it's all in its package, I'm looking at the side of the loaf of bread here, and sliced bread, clearly, maybe seedy bread, like whole wheat. That's what I eat in my house, whole wheat bread. And then we go all the way down to the end, and we have that, that three-dimensional face, or that sideways face of that last piece of bread, and it's all in the bag. So we have slices of bread. Now that's clearly a loaf. It has a volume to it, measured in, I don't know, milliliters or something, centimeters cubed perhaps. But this bread, if you take it apart and you just look at one slice of bread, so this one slice of bread as we face it towards ourselves, this has a surface area or an area of a face. And we can calculate that area. We might know it. Today we're going to know it based on geometric formulas, squares, triangles, whatnot, semicircles sometimes. But it also, if you turned and looked at the little side of the bread, that piece of bread also has a teeny little bit of width to it. And so the width of that slice of bread down here is what we're going to call our dx width. It's a little slice. When I stack them all up, I go from left to right along my loaf of bread, starting over at the left-hand side and ending at the right-hand side, and I have a whole bunch of slices of bread added up. Now, can you see that volume is three-dimensional? And that what I have is an area, which is a square dimension, and my third dimension comes from my additional width, which is linear. Now in a combined squared and linear, I get 3D and I get a volume. I don't know if that helps, but I like the slice of bread because I can see it on its side. The three basic methods for finding volume: cross-section, that's what we're using today. We're going to use this idea of this cross-sectional slice. We will rotate with circles and get washers. We will not go to shells. That will be the section we don't do. Here's a shape. Interesting. So we see on the XY axis now in front of us. All right, so here we have an example. We see the XY axis is described, shaded here, an area shaded by our f of x, which is a semicircle. And we see those little rectangles again, up and down, those rectangles like we did in the last section, described, and we see these popping out slices now described below. The three-dimensional graph that you have there shows each of those slices that we have here stacked up one upon another as we go from left to right across that semicircle. So the slices themselves, as you see in this picture, the slices will change in their size. But no matter where we go, in this case, this picture is describing square slices. Every single area of every single piece is the shape of a square. So the area here can be defined by our formula for a square, side times side. Or in this case, because I have my little square described to me over here, I can take f of x as one side, and the other side will be f of x too. So we're going to be stacking those slices up, accumulating a volume. And because we have the length of a square being f of x, I might call it height based on the fact that we see that the f of x has a height or a base. In this case, it doesn't matter so much because it's a square. But in the three-dimensional picture, where's f of x? F of x is down here. So your f of x is actually the base of each square. And so we don't see this. This is down underneath the shape, but the base of the square is f of x. And then we get the cross-sectional area of a square is side times side, y squared, or f of x squared. If we stack all those up, the volume of each slice is the area of the shape times delta x. And so we can integrate to find the volume. So the volume that we see here, this is describing just a arbitrary semicircle based with a radius a. It could be any number. But I want you to focus on something with this entire section. Volume is going to be defined as a definite integral, and from a to b, because we have boundaries on that integral, of some area times dx. Volume is three-dimensional again. Area times dx is going to give us volume. What we see in this example is that the area is here, and then the dx, the third dimension, is here. Note that the area has a square on it. We should have a square value. We should have some square value of x all the time when we think of area. Feet squared, inches squared, meters squared. Note that because this is a symmetrical area, we can write the integral in two different ways. Either we can sum from negative a to a, or we can double from 0 to a. And that just might be convenient for you when you're figuring out how to answer these questions to, kind of eliminate some of the bugs in integrating. Clearly, the second integral is going to be easier because it's always easier to plug in a 0 than it is to plug in two different numbers, especially with negatives. All right, so remember, volume equals the integral from a to b of the area times delta x. We'll see that over and over. So here's our first example, not 1, it's number 2 on your paper. But we have a circular base. Now the base is described because we have it sitting on the paper. I mean, the paper is flat on the table. So the base is flat on the table. So the base is a circular base. And popping up out of that circular base are squares. And the squares are described to be perpendicular to the x-axis. Now what I want you to do when you see this, and you actually see drawn on your paper, that perpendicular to the x-axis is important. It's going to tell us that we need to make sure that we draw our rectangles perpendicular to the x-axis as you see here. That is going to indicate to me whether it's a dx or a dy type problem. This is a delta x. So each of those slices is going to have a delta x. That's going to tell me that my integral itself has, as its guts, or the integrand, it has a y inside or an x inside. I'm going to drop out of this for a second and show you this on an activity. Yes, here. Okay, so here's the idea that we see. I'm going to show it to you on this little Geometry Sketchpad app. Here's the circle. It has r and negative r as the radius, but that's because I can change it on this function, on this program. But I'm setting r to be 2. Now that is our picture on our example, on example 2. It has that x squared plus y squared equals 4, where in this case the radius is 2 because we have a 4 squared here. So we have the graph of the circle. I want to show you those chords. Now chords means the segments of the circle that go from one side of the circle to the other. So here's those chords, those little rectangles drawn up and down, perpendicular to the x-axis. So I'm going to drop this down flat. It's flat in front of you right now, but if we see it in a three-dimensional sense, we're going to think of it as, oh, like that. And here's a square. I'm going to show you 4 of them as they come out of, pop up out of the graph. So each of those squares pops up. The squares change because the side itself is changing based on the function that we see on the paper, the circular shape. If we take that square and see it as it goes along from negative r to r, or negative 2 to 2, we see that the square area changes, but it's always going to just be base times height. Overall, the solid looks like this, and that's what we see on the paper. It's different in the orientation on the paper. I have it slightly rotated, but we see those 4 squares again inside, and we can see how that square comes along from left to right, and it carves out, or it makes this shape. Kind of like a tent, those like party tents. All right, so I'm going to stop here at the end, but I want you to notice on here, volume of the entire solid equals 42.67. Write that down on your paper for this example. That's going to be our answer, 42.67. So let's calculate it now. I'm going to write that down on my paper, 42.67. I'm going to check to see if we get that as an answer. Funny that this program actually gives me the value that I'm looking to find. So let's go back over here and see where we are. There's our little rectangle there, it just came in. Here's our function, the full circle. Now, in order to integrate, though, we can't integrate this, we have to solve for a variable, one or the other. But the area of one square is side squared, and I always like to jot that down. Square equals side squared, the area of the square. Each side is 2y units long. So why is it 2y units long? Oh, because if I look at that square that pops up, or that rectangle that I've drawn on my diagram right here, that is y from 0 to the top, and then another distance of y from 0 to the bottom. Think again of top minus bottom. The top is y, the bottom is negative y, so this distance of a chord, as we drew them in before, each chord is going to be double the y height. Most of the time, we'll be dealing with semicircles rather than a full circle. If we had a semicircle, we'd only be using the height of y rather than 2y. If we take 2y and square it, we get 4y squared. Okay, that's good. The volume is the integral of all the areas. Oh wait, the volume, I'm going to write it again, is the integral of all of the areas times the thickness dx, from the left to the right. So they talk about, we can use symmetry, we can simplify this, since we don't have differing shapes from left to right. We might use symmetry again here, just to do from 0 over to 2, and just get this quadrant on the top. We might do just 1/4 and multiply it by 4. So let's see how we can set it up. This setup has as its beginning, remember we just came from the last slide over here, we had 4y squared as our area. So our volume is equal to the integral of the area. So I'm going to write that up here. The volume is equal to the integral of the area, and the area was 4y squared times the thickness dx. Now that is right there wrong, because I have a mixed y and x. We have that -2 to 2 to represent the whole set of squares as we go from the left to the right. But see that the y and the x don't match? The bounds are x's, -2, 2. The dx is an x. We need that y squared to turn into an x function. And so in this next, oh gosh, all right, so first we took the 4 out, and then we simplified by going, instead of from -2 to 2, we're just going to go from 0 to 2 and double that value. So there's some simplification going on here. So we have that 8 as a coefficient. But now we take the y out and replace it with 4 minus x squared. Remember, original function x squared plus y squared equals 4. We can manipulate it and say y squared equals 4 minus x squared. So now we have x's everywhere. So let's see how that is equal to 128 thirds. We can integrate this. It says that most of the problems will be set up only. You'll see this on the AP test. It'll say, set up the integral that represents the volume, but do not evaluate. And which means we would just be done with any of these above statements. If we use the calculator, we would certainly easily type any of those 4 options into the calculator, as long as you have them all in terms of the same variable x, and we can get 128 thirds. But let's just go ahead and do it by hand. Integrating this by hand, so we're going to have 4 integrates to 4x minus x cubed over 3, and I'm going to evaluate this from 0 to 2. Okay, so we've got 8 times the quantity. We're going to plug in the top first. So I got 4 times 2 minus 2 cubed over 3. There's your plug in there 2 minus, oh, plug in the 0. Very good. 2, plug in the top, 0, plug in the bottom, and simplify. So I've got 4 times 2 is 8 minus 8 thirds times 8 in the front. Need a common denominator of 3. So I've got 24 minus 8 over 3, all times 8. Notice that I'm just waiting to the end to multiply by 8. You could distribute it through anywhere. So 24 minus 8 is 16 thirds. And 16 times 8, yep, that's 128 thirds. Now remember that I told you to write down the answer. This is equal to 42.67, which is what that computer program showed me. Excellent. If this was done in your calculator, you would probably have to go math enter enter to get yourself back to 128 thirds. But if we did it on the calculator, make sure you use parentheses clearly to help yourself in case the argument inside the integral. Be really careful with those parentheses. I will always encourage you, if you are going to do volumes on the calculator or areas on the calculator, write down the integral first. Do the entire integral on your paper before you pick up the calculator. Do not try to do it on the calculator and neglect to write it on your paper. All right, so let's try another one. Next one is going to take the same circular base in example 3 on your paper. Cross sections that are isosceles triangles perpendicular to the x-axis. So note that the little rectangle, the imaginary one rectangle, is drawn in there perpendicular to the x-axis. And we have we have an isosceles triangle where the altitude is equal to the base. Now that's going to be helpful to me because as I take my triangle, I remember from the last problem we had that chord being measured. Remember, one chord was 2y long. Let me just go ahead and do this right now. This function, x squared plus y squared equals 4, we keep on using it as x squared plus y squared equals 4, but we could also write y equals plus or minus the square root of 4 minus x squared plus or minus. So that's the other version of the circle we see. We see the top circle and the bottom circle there. Our base of our, excuse me, the base of the triangle is 2y, and the altitude is equal to the base. Well, that's beautiful because now I have a formula for a triangle. Now, do you remember what the formula for a triangle is, I hope? 1/2 base times height. Excellent. And if we plug in those values, our base is 2y, our height is 2y, and there's your 1/2 base times height, simplified to 2y squared. Now this, again, is y squared, or the square of the square root. This is the area of the the isosceles triangle that we have. Now that's going to create this shape that we see right here. Should we go look at it? Yes, let's go look at it happen. So we have equilateral triangles this time. Chords again, drop the axis down. Let's see those 4 triangles. Not exactly going to give me the same area this time as our answer because these are equilateral triangles where we have, not equilateral, we have altitude is equal to the base. And we see 4 triangles as they run through. Let's create the solid. And the solid is going to be coming from the left to the right. You see it as almost conical on your paper, but when it develops this way, it's not quite conical. It's more, more like a tent again. They're all tents. So there's 4 triangles within that solid. Again, 18.48 is not going to work for us. We have a different type of triangle given to us. But let's get through here back to where we were. So the volume is, again, area, the integral of area times the thickness dx. This keeps coming back. And so here's our integral. We can use the integral that we have on the left, and we can grab the calculator, we can type it in, or again, the problem might say, write the integral that represents the volume, but do not evaluate. And that would be either one of these 2. I don't know if you want to use symmetry. The integral on the right shows the symmetrical doubling of the circle and just going from 0 to 2. Might be easier. Clearly it might be easier, as we saw earlier on our evaluating. Plugging in 0 is beautiful. Let's just move on to another example there. On your next page, you have triangular cross sections. This time I'm going to have a 45, 45, 90 triangle. And the 45, 45, 90 triangle has one leg on the XY plane. So what do you have? What kind of picture can you see? Now that triangle that we have, 45, 45, 90 triangle, looks kind of like this. And one leg, and remember the leg is not the hypotenuse, is on the XY plane. That's going to be, the leg is here, perpendicular to the x-axis. All right, And as we think about one triangular cross-section, what is the area? Oh, okay, so let me think of that again. Oh, this is partially wrong. Okay, that's not right. This is a leg, it's represented here, and that leg is actually equal to 2y. So our area of our triangle is not 1/2 yy, it's 1/2 2y, 2y. Or 2y squared. Be careful about how you develop your area formula. It'll make all the difference in the world in our problem, because this is going to be part of your integrand. Remember what y squared is? Y squared is equal to 4 minus x squared. All right, so let's set that one up. We think of this again one more time as volume is equal to the integral of the area. And we've developed the area above, so we can just put in 2y squared times dx from the left to the right. And as before, we can factor out that 2, we can replace and match our variables, so it's 4 minus x squared dx. And again, as shown before, we could simply go from 0 to 2 and double, so the 2 gets doubled to a 4, 4 minus x squared. Dx. Again, area times dx equals volume. So that's the setup for this one. I'm not going to integrate. I love integrating, but I need to move on. I need to go to Florida. Oh, wrong. Ignore that. I like mine better. A different example. Now we're going to go away from that little circle we've been using over and over again. The base can be described by anything for us. So this problem, number 5, has a parabola y equals x squared, bounded by the line y equals 9. So pay attention to that. As we're given information in the problem, we have the parabola y equals x squared and the line y equals 9. And so graphing is very important. Super important, please. Remember graphing all of these basic things. And then we have given to us, I see the bounded region. I see the left, the right, the top, the bottom. So that's our base. But we're going to pop semicircular cross sections perpendicular to the y-axis. And you note on your paper, we have that perpendicular to the y-axis shape in there. So kind of looks like we should have a dy here instead. And again, it looks like there's symmetry. So I think again, we're just going to go ahead and simplify this down to a much more easy integral. And the integral this time is going to be from 0 over to whatever intersection point we have here. Might be from 0 to here, but think again, if we think in dy, we actually want to go from bottom to top. So we'll see what happens as we develop it. But this is what the picture is going to look like. Notice that over here we have little semicircles popping up out of the bottom. And I don't have the picture of this one like I did on the other, so I'm going to sketch a couple in here so you can sketch them in. As we go from 0 up to 9, those little semicircles are slices of this cornucopia looking thing. So there's my little semicircle. This is the area. This is the area that I'm going to have to get semicircular cross sections. I'm going to need an area formula for this little shape. So as we look at the shape and where it pops up out of our diagram, we have the diameter of this semicircle is 2x, because here's my x from left to right, and of course all the way across it's twice x. The diameter is going to be twice x. Which means if I cut that back down to a radius of a semicircle, radius is x. Now, when we have a semicircle or a regular circle, we're talking about pi r squared for our area. The equation of the parabola is y equals x squared. We need it in terms of y because we're talking about perpendicular to the y-axis. So we're going to take our function and we're going to have to make sure everything is in terms of y. So let's look at that. First, we solve our y equals x squared for x equals the square root of y. That is only going to be 1/2 of our parabola. And when we look at that radius that we developed being x long, we only need a radius to be 1/2 of the parabola, or this square root of y. So one cross-sectional slice in a semicircle comes from the formula for a semicircle, 1/2 pi r squared. So we have pi r squared, we developed our x equals our radius, and then we see over here we can turn that into a y function, square root of y. So you see the simplification here, area is 1/2 pi y. And there you go, you get your integral pi over 2. Now we're taking that pi, 1/2 pi, and turning it into pi over 2. And we're calculating, because we have y's and dy's, note that the boundaries are not x boundaries, they're y boundaries. We start out at 0 and we sum all the way up to 9. So every value is in terms of y. And that's not a hard thing to calculate. But whether you do it on the calculator or whether you do it by hand, we do have to remember that those limits of integration are in terms of y. Same parabolic base. One more example here with this cross-sectional area perpendicular to the y-axis again. But this time, instead of semicircles, I want the areas to be isosceles right triangles with a hypotenuse on the parabolic base. This one, you know, if you want to skip it, I'm pretty okay with it. Fast forward a little bit. This hypotenuse being on the base that's described right here means that I'm going to have to know something about right triangles and 45, 45, 90, and figuring out, if I wanted to find the area of that triangle, I know what the base is. The base is 2x, the distance across from left to right, but I don't know what that height is. Okay, so let's scroll through this. If you wanted to skip it, please feel free. I don't think this problem occurs on AP anymore because nobody knows how to use 45, 45, 90 to figure this all out. So the hypotenuse is 2x, we talked about that. Well, if you think of the altitude here of this triangle, it's the hypotenuse, and this is 1/2 of the hypotenuse, and this is a √2 ratio with the sides of 1. 2 over √2, √2x. Clearly we have to go back to geometry to figure that all out, but we need to put everything in terms of y. X equals root y, so we have a side of √2y. So the area of the triangle is 1/2 the base times the height. And we have some simplification. We have the volume, which is integrating the area times dy from 0 to 9. You're not going to see this one, I promise you. However, we like semicircles. So we see in example 7, same parabolic base, same exact parabolic base here, but the cross sections are semicircles perpendicular to the x-axis. So the way I usually develop this, I read my perpendicular to the x-axis, I draw in that one representative rectangle, and I know I need a semicircle area formula. So this is what I pull out of the problem. Semicircle area, that's going to be the integrand times dx, because I have a dx representative here for the rectangle. So let's see that. This semicircle base this time is in this shape, not flat left to right, but instead it's up and down. Now think about this. If this is representing the up and down over here, we're going to use this diameter of the semicircle, and it's going to be top function minus the bottom function. We're going back to that idea of area of top minus bottom again. So the diameter here we'll see comes up as top minus bottom. And we want in terms of x's, because we have a representative delta x segment. So here's our top 9 minus our parabola x squared bottom to be the diameter. Now when we calculate the area of this semicircle, we're calculating half of pi r squared. So we're going to take that diameter and we're going to turn it into a radius. So we have a radius defined for us. That it comes from me knowing the semicircle area is 1/2 pi r squared. So I need to know what I need to find. I knew 1/2 pi r squared is the area, so I went looking for the radius. So here's my radius. And 1/2 pi is out in front, r squared. We see that again now in terms of the function, and we have a pi over 2 put together. Now watch what happens next. If we want to integrate this, clearly we can just integrate it as it is. From left to right, I don't know if you know, but the left bound and the right bound, where this base is defined, think about it for a second. That's a line of 9 and x squared. And so this is going to be from -3 to 3, I believe, thinking that that's what the x boundaries are going to be on my integrand. But watch what happens if we take this entire thing and put it into the integral. Where did the pi over 8 come from? Also, note that instead of going from -3 to 3, we can simplify ourselves and just do twice the 0 to 3 region. So we're doing 2 times the 0 to 3. But where did the pi over 8 come from? Now, you may have to match this up multiple choice, and we would need to know this, but there's the 1/2 pi, and then when we look at the r squared, half of a circle squared becomes an additional 1/4. So we have 1/2, 1/2, 1/2, or this pi over 8, or 1/8. Doubling it comes from halving the distance on the axis, x-axis. You could still go from -3 to 3. You just not include this 2 in front. But here's our 1/2 pi, and then 1/2 squared. And here's the other part of your radius. Oh, should we do this one on the calculator? Sure, why not? Make sure we can get this all on the calculator. I may actually go back to integrating even something that I would set up. This is certainly easier for integrating by hand. We've reduced out the duplication of certain things, so it's easier to do it by hand. But if I'm going to do this one on the calculator, I frankly would encourage you to just do volume is the integral from left to right, that's -3 to 3, of the area, which is pi over 2 times 1/2 times 9 minus x squared. So there's pi r squared, or 1/2 pi r squared dx. Now in order to do this in the calculator, if you do have the more difficult formula here, I need to remember that if I touch that calculator, it's going to force me to do this. So I want to know that there's an additional set of parentheses in there. So let's look at this one on the calculator with the version maybe that we have without simplifying into the pi over 8. So alpha y equals, or alpha window, function, -3 to 3. And here's where I'm talking about. I got to put all that stuff in here. So I need a pi over 2. So there's my 1/2. And now I'm going to say 1/2 pi r squared. So here's my r, which is, again, 1/2 the diameter. So the diameter that we had was 9 minus x squared. So there's a radius right there, 1/2 9 minus x squared. Got to close my radius, so now I'm looking at this, and if you're in computer science, you know what I mean? This is the end of my radius, and I need to square this. And then we have the end of the integral. So here's the open and closed integral dx. Lots. Notice that everything is gone now. You lost the beginning. So it's harder to type these in because they're very intense. 101.787. 1/2 pi r squared. So kind of an intense setup on the calculator, and definitely have errors in just typing that in. All right, I think I've had enough. We can look at this next cross-sectional area with a top and a bottom again. This one's not so bad. One last example. What am I picking out? I'm picking out my top and my bottom. So I'm going to point out here in the problem that even before I had the graph, I probably should know this function actually would be y equals 2 root x. I know I have a rational function, and then I have also a line. And the line goes under the rational function. So I have a top and a bottom of a region. That's my base. And it says that the perpendicular to the y-axis, so this is important for me. Do you remember why this is important? That allows me to know my representative rectangle, which is going to give me, I need to have everything in terms of dx. Then I go find back again, we're talking about a volume. And the volume is created by rectangles with the length and the width half the length. So I have to figure out how to write this. Rectangle. Now we have a rectangle, and the width is half the length. Width. So I have my length here. The length is what, oh, I should probably turn that. The length is my piece perpendicular to the x-axis, so I'm going to call this length. And the width of the rectangle, this width, is 1/2 the length. So my rectangles are going to look like this. Now that is an odd picture that we see below. What we see is here's a width, and there's, or sorry, the first piece I drew, here's the length. The lengths are these pieces here. And this width is half of the length. So you see that it's kind of shorter, the so-called width. Now, if you look at that picture, agree with me, it looks like that's a height. But that's only because we're talking about length and width of a rectangle, so we can identify which is which. It's the piece up above that said that the length is perpendicular to the x-axis that tells me that that perpendicular piece right there is what we're calling a length. So let's talk about what the area of a rectangle is. It's length times width. So the area is going to be length, and the length of my rectangle as I've had it drawn in the graph, isn't it just the blue minus the red, or the top minus the bottom? Well, of course it is, Ms. Grisho. The length is the top minus the bottom. And so that is going to be my first part of my area. Area is 2 root x minus x. times 1/2 of that length again, 2 root x minus x. So this is the area of that rectangle I have described. Clearly, this is the hardest part of the problem, is just trying to identify an area formula. Once we have that, the rest of it is really a piece of cake. Volume is equal to the integral of the area. Now let's look at that area I just written there more clearly. This time I can see how that simplifies. I have a 1/2 and I have 2 root x minus x twice, so I'm just going to square that. So here's the integral of the area times the width of dx, creates the volume. Do have to think about my boundaries on this, and it's clear that this little base shape starts out at 0, and as I move across to the other intersection, well, where is 2 root x equal to x? So I can figure that out. 2 root x is equal to x. Maybe square both sides. 4x is equal to x squared. And if we think about the fact that we've already gotten the 0, we can take an x out of both sides of that equation, and we can have, if we factor an x out of both sides, we have x equals 4. So this over here, this boundary is at 4. If you had a calculator, piece of cake. Graph the two functions and calculate the intersection. So we can create that volume there, that integral, and we could solve that. Perhaps set up and not solve. Perhaps set up and use your calculator to solve. It's going to be a little more difficult to do integration here. If you remember your integration methods, I have too much going on in the integrand. I'm going to use a square and FOIL this out, or distribute that interior out. Certainly not going to use any U sub or method like that. If we had to do it by hand, expand and then integrate. But even still, we'd be integrating a square root, which is not fun right now. Okay, so there's the end of that one. We have one more on our paper. I'm going to leave it for you. See if you can set that one up. You also have one other. I've been here the whole time. You also have one other document that I've uploaded for you, and I'm not sure exactly what it says at the top, but it's a series of problems that ask you to use a calculator or not using a calculator to develop some review of the problems that we have here on these two lessons put together. Some areas, top minus bottom, some volumes with different shapes. But pay attention, because it'll say in there, set up but do not evaluate. Okay, so please follow those directions and attempt to do that other worksheet so that we come back, you have your worksheet done with as many of the attempts as possible, and we have saved 2 days on our time, so we can go and do some more AP prep afterwards at the end of this month. All right, so have a great break. Checking out.